General relativity, step by step, number 27. I've lost the thing, so there's my knot. Right, we've got a vector v, which I'm going to write like this: v1 e1 plus v2 e2 plus v3 e3, where the e1, e2, e3 form a basis, but they're not necessarily orthogonal, and we've defined a an object G, which is called a metric tensor ij equals ei dot ej. So we've got this nice little concept that we've been playing with here. Now I've also set out a conjugate basis, which I'm going to write like this: omega 1, omega 2, omega 3. And this is a conjugate basis, conjugate basis. And we've specified that omega I, oh no, the e's have got the downstairs ones, dot omega j upstairs equals 1 if I equals j and 0 if I not equal to j. And we write that ei dot omega j equals, and then a new concept, delta ij, and that's called a Kronecker delta. It's the same thing. These are the same thing here. So when the indices I and j match, it's equal to 1, and if they don't match, it's to 0. So this is a very useful object indeed, and we'll see later why we write it in this rather peculiar way, rather than with two downstairs indices. There's a cat there, just meowing away. Okay, so what am I going to do? Let's have a look at vector w, which I'm going to write like this. It's going to be w1 omega 1 plus w2 omega, oh, it's easy to get this wrong, omega, oh, I've got it wrong again, w2 omega 2 plus w3 omega 3. And from my notation here and here and here, we can see that the w's, the w1, w2 and w3, they're just numbers. They're just real numbers, and we're putting it together a vector by taking its components in these three directions here. So if I want to take a product of w with itself, w dot w, well, I'll write it out. It's w1 omega 1 plus w2 omega 2. I'm trying to write it neatly. w3 omega 3 dot, oh, I need a bracket. Dot the same thing, w1 omega 1 plus, can I do it? Can I fit it there? Let's see if I can do that. Plus w2 omega 2 plus w3 omega 3. It's very easy to get this the wrong way around, or put numbers where, put subscripts where there should be superscripts and so forth. Equals. And then what I'm going to do is to use the distributivity of the dot product, and it's w1 omega 1 dot omega 1 for this term times that term, plus, and then w1 omega 1, oh, I've written it the other way, w2 omega 1 dot omega 2 for this term times this term, plus all the way along. And so what I'm going to do, of course, is I'm going to write it using the summation convention. I'm going to write this sigma over I and j, wi wj times omega I dot omega j. And this thing here I'm going to call also going to call it a metric tensor, but I'm going to write upstairs indices instead of downstairs indices. Last time, have I got it on this screencast? Yes. Last time, when we talked about the metric tensor, we were multiplying the e's, ei dot ej, and that gave us this thing called g. And now I'm going to use the conjugate basis, the omegas, and I'm going to get a g, but with two upstairs indices, d, I, j. And the way to think about it is that w dot w equals wi wj Gij, with an implicit summation that we don't need to say because we've got a repeated index I and a repeated index j. So by the Einstein summation convention, we don't need to mess around with sigma ij. We can just get rid of that. Now what I want to do is to bracket this in a slightly different way. It's wi, and then I'm going to put the brackets here, wj, gij, and I'm going to call this thing w, well the j's are summed, you see it's summed over j, so it's wi. So the way to think about that is that we've got w with a downstairs index, I'll call it a j, I'll call it a j, then we multiply by this metric tensor ij, and we've got a thing which I'm going to call w with the upstairs index. So effectively what we've done, we've taken a downstairs index, we've multiplied it by our g with upstairs indices, and we've taken a downstairs index and turned it into an upstairs index, which is quite a nice thing to do. And if you'll remember from a previous screencast, we got a vector v with an upstairs index. We could multiply by g with two downstairs indices and turn it into a downstairs index. So we can take an index and lower it using this form of the metric tensor, and we can take an index here, we can take a downstairs index and turn it into an upstairs index. I know the proper words are contravariant and covariant, but frankly you forget that when you're working with relativity. You just consider downstairs and upstairs indices and you make sure everything balances. So yes, I know they're contravariant and covariant indices, but that terminology is it's awkward and unnatural for a lot of people, including me. So I talk about downstairs, I'll talk about upstairs indices and downstairs indices. And we can go upstairs and downstairs by multiplying by the metric tensors. Now it's as obvious as anything can be that if I've got an operator to take an index upstairs and take an index downstairs, I really should be checking that if I move an index upstairs and move an index downstairs, that I've got back to where I started. And so what I want to think about is what this matrix product here is, G, J, K. This one here taking an index downstairs and this one putting it back upstairs again. And that should be equal to the identity element. What we're trying to show is that if I have a matrix with an upstairs index and I say I want it down, that's taken me to a downstairs index. If I then say G, J, K, what I want that to be equal to is V K, of course, because the J's are summed here and the K is free, and so that K is this K here. Actually, I'll draw them in different colours. It's sometimes very helpful, or a lot of people have said it's very helpful to put them in colours, and sometimes I'll write them in slightly different colours myself. When that's K there, so that's a free index. But what I'm going to draw in a slightly different colour, let's try blue. I'm going to draw the J in blue, J, with the understanding that that's summed. These are summed indices here, and of course the I is repeated, so that's summed as well. Let me just grab that, draw that in a different colour because it's a different yellow. Probably a poor choice of colour, but never mind. That's I, and that was an I downstairs. So the upstairs sum with the downstairs. That's quite nice. So what that means is, if this is right, actually I'm going to go back to black before I forget. But what that means is we want this. We want this equality. We want that equality because what we've done is we've taken an index and moved it downstairs, and then I've moved it back up again, and we should really get back to where we started. So what that means in mathematical notation is I'm trying to prove that this is the case. Gij, G, J, K equals delta for the Kronecker delta, the J's are summed, I, K. So if I can rephrase that, if I've got an index upstairs and then I multiply it by G, I, J, G, oh dear, my writing, G, J, K, I want that to be equal to V, I, which is what we had before, there it is, bonk, times this thing here, delta I, K. Now, this is the genius of tensor calculus. The thing is that when you write it, it's absolutely magic. I'm going to switch over to red, just to remind myself, which one was it? It was an I, not a J. That's an I, just to remind myself that this is summed here. Go back to black. And that will equal VK, which is what we specified here. So why is that? That's because this one here kills K not being equal to I. So we're summing across it, summing across it, summing across it. It's only when I equals K that it survives being multiplied by my Kronecker delta. And that's why we've got this here, because that means we're multiplying. If I equals K, that means multiplying by 1, which means that we can just write it like that. So what I need to do, I need to prove that Gij downstairs multiplied by Gjk upstairs equals Kronecker delta, J's have gone, Ik. Of course, this is summed over J, but I don't need to say that because of the Einstein summation convention. So I need to prove this. How do I do that? Well, what do we know about it? Well, so far, what have we got? We've got that omega I dot Ej equals Kronecker delta Ij. We know that. We know that, what else do we know? We know that Ei dot Ej, these are vectors, equals metric tensor Ij. And our new one is omega I with upstairs indices, these are the conjugate basis, dot omega j equals Gij with an upstairs index. And so what we've got is a whole bunch of linking equations that link these different concepts together. And what we need to do is to use it use these facts in some different way. We've got this one, we've got this one, and we've got this one. I'll see if I can do it all on the same page. Okay. Well, let's start with this one. We've got omega I dot Ej equals, with lots of space around it because I'm going to multiply it by various things, delta Ij. That's the Kronecker delta there. And what I'm going to do is I'm going to multiply on the left by Gjk down there, Gjk. And before I get too excited and too sort of carried away with the algebra, I just want you to observe casually how the Einstein summation convention is just working for us, because really there are brackets there, but nevertheless we are summing across this I which is inside the bracket with that I which is down there. The summation convention just works silently for us, and we don't need to worry about brackets or where they're placed or anything. We can just write the metric tensor out. Okay, well, what's this equal to? Well, that's equal to, well, we'll come up with expressions for all of these. Well, by the picking out argument, this again this here kills I not equal to j, because it's the Kronecker delta. So what that does, that tells me that I can forget, because I'm summing over I, it's only when I equals j that this matters. So that's just equal to Gjk. And what have I got here? Gjik omega I dot Ej equals that. Well, that's quite nice. And that equals, of course, Ej dot Ek by definition. That's nice. And now I've got an Ej on both sides. I've got one here and one here as well. Well, that's quite nice. So what I'm going to do, I'm going to factorize it by Ej, and I'm going to take it over to the other side. I'll do it in 1K. I'll do it in line by line dot Ej minus, all I'm doing is taking this thing over the other side, changes its sign, Ej. Actually, I'm going to swap it over as well. Ek dot Ej. It's not very neatly written. Ek dot Ej. And that equals 0. All I've done is taken this term here and put it on the other side, and I've written them the other way around because dot product is symmetrical. Now I'm going to factorize it. Ej dot this thing in here, Gjik omega I minus Ek equals 0. Now there's quite a lot going on here. This is, remember it's summed over I. I may as well put the summation back in. sigma I. After a while, you don't need to do that. After a while, you just see the summation sort of floating there notationally, and you don't need to put it in. But I'm going to put it in anyway. What this does, it shows me that I can, this k here is what you call a free index. It means I can substitute what I like. Substitute k equals 1 and it will work, k equals 2 and it'll work, and k equals 3 and it'll work. And if I'm working in a 4-dimensional space, I can say k equals 4 or k equals 5, as high as I like. It'll work for any k. So I'm going to rewrite that expression there as tk, t equals something, and I'm going to say that tk dot ej, that's a vector, equals 0. Why is this a vector? Because it's a product of vectors. Because it's a sum of vectors. This is dead obviously a vector. Here's another vector, but what we're doing is multiplying it matrix-wise by a whole bunch of scalars, so it's still a vector. So this thing is a vector. tk is a vector. And I can put k equals 1, 2, 3, or whatever I want in there. So let me rewrite this term here. That's tk dot ej equals 0 for all k. And actually for all j as well. Well, that's nice. So what that tells me, because ej equal, because I'll move out of abstract notation. E1, E2, E3 is a basis. What that tells me is that tk equals 0, the 0 vector, for any k. Why? Because whatever this thing is, when we take a dot product with any of the ej's, we get 0. So tk equals 0 for any k. What was t again? Well, I'll go back up here. It's this thing here. So let's write that out again. Sigma over I, which you don't really need, gij omega I, gi, what was it? Ik omega I. Ik omega I minus ek equals 0, again for any k. So that tells me that sigma over I, g, ik omega I equals ek. And you'll remember what I want to do is to link g with 2 downstairs indices to g with 2 upstairs indices. Okay, and I've got my downstairs, my g with downstairs indices. I need somehow to create a metric tensor with 2 upstairs indices, like that. And what do we know about the upstairs indices? G with the upstairs indices. Well, we should have the definition of it somewhere. Oh, here. We've got a definition of it somewhere. Here it is. It's the dot product of my conjugate basis elements, omega I dot omega j equals g with my upstairs indices. So I'm going to have to use that. I'll just write it down so I don't forget it. We've got gij equals omega I dot omega j. Well, I need to get this with upstairs indices, and I've got one here. Here it is. I've got an omega with an upstairs index. So what I need to do is to multiply it by another omega and see what happens. So I'm going to get rid of that. I'm going to get rid of that summation. We're grown-ups. We know what we're doing. We're adults. G, I, K, omega I underscore equals E, K. And what I want to do is to take a dot product with, let's get this straight. We've got a K downstairs. I want to take a dot product with, I want to sum over the K's, so I need to take a dot product with. I'm struggling here because I'm going to write that K in, and I guess we need another L there. Oh no, hang on a minute, I'm doing it completely wrong. I need to take a dot product with L, let's just say. There we go. So I need to take a dot product on this other side here, which is omega L. Yes, I want you to see how difficult that process was there, because what I'm wanting to do is, let me do that whole process again. Let me get rid of this here. What I want to do is I want to observe. I want to use this. What I want is G with two upstairs indices. And the definition of G with two upstairs indices is it's omega something dot omega with something else, and that's I and J. And I've got half of that here. So I'm going to multiply here by, I'm going to have to be a little bit careful with my letters. I said L last time, let's call it a J. I think J might work. But I've got, that's a dot product, and I've got to do the same on the right hand side, omega J. Okay, so what that tells me is what I've got is I've bracketed it this way, but now I'm going, because it's associative, I'm going to bracket it the other way. That's no problem. Everything's finite, everything's nice. These are numbers. G, I, K, because we had it last time. G, I, J, upstairs by definition from here. Equals EK dot omega J, just copying that. But we know that the E's and the omegas are conjugate bases to one another. They're conjugate bases to each other, and I have that right up at the top here. If I go back. There it is. No, it's this one here. There it is. They are conjugate bases to each other, and finally I'm using that fact, or I'm reusing that fact, I guess. Let's just go back together. Equals delta JK equals 1 if J equals K, and 0 for J not equal to K. So, G, I, K, G, I, L equals delta JK. Oh, that's it. So what that tells me is that if I've got a vector with an upstairs index, and then I say, no, I'm going to turn it into a downstairs index, see the summation over I, and now I'm going to turn it into an upstairs index. Hang on a minute, that should be a J, not an L. That should be a J. J. So this takes it down, this takes it back up again. That equals VI times delta. Actually, I'm not going to write the delta in, I'm just going to do it step by step. This is general relativity step by step. G, I, K, G, K, J. I want you to see how careful I've got to be to get the index matching. Here, I was getting myself confused because we're summing over J and we're summing over I, and so we had a J left and I was getting all confused. So what we needed to do is to write it out step by step. What I'm going to do is to change the bracketing here because everything's associative. It's VI because we had that before. And then this thing here is a delta IJ from this rule here, except it's a little bit different. What I'm doing here is I'm summing on this term. Ooh, I need to do that. Just a minute. Do that. What I'm doing here is, if I go to a red colour, then we can see it more easily. I'm summing over the K. There they are. And what's free? We've got an I free, which is on the downstairs side, so that's this one here. We've got a K upstairs, which is this one here. All I've done is use this rule here that I established at such great difficulty, but I'm switching the letters around. Here I'm summing over I, and here I'm summing over K. So it doesn't matter, it's still the same thing. It's just I've got different labels for my terms, that's all. So if I go back to what I've got, bonk, we've got this equals VI delta IJ summed over I. The summation convention is our friend, it's working for us. And of course, this term here picks out the term where I equals J, so it's equal to VJ. So let's go through this whole process again. Here's VI from up here. I say I don't want that index upstairs, I want it downstairs, so I multiply by the metric tensor with downstairs indices. And then I change my mind, I want to put it back up again. Kj equals this thing here, Vj. So it's the same thing, except that we've gone through all this complicated process by summing through I, which is here, that's summed there. Different colour for the different summation, I'll go to green. We're summing over K, which is this one here, and the J, which I'll indicate with yellow, the J is just there on its own, unchanged. So all it is a notational change. I've changed an I to a J, it's upstairs, but it's the same symbol on the left and the right hand side. So I know I'm making heavy weather of this, but it's really, really, really important. IK GKJ equals delta IJ. The other way of thinking about it is that if you interpret these symbols here as matrices, then they are matrix inverses. So the matrix M, no, it doesn't matter, I can just write it out, GIK, as a matrix multiplication by GKJ. See how we're summing over the columns and the rows here? So it corresponds to regular matrix multiplication as a matrix. These guys are matrix inverses. What a fantastic result. They're matrix inverses, so when you multiply them as matrices, they give you the identity matrix. Just that. 0, 1, and I guess you could put more zeros on either side if you really wanted to. So that's equal to the matrix product of these guys here, which is the identity matrix, of course, which is another way of saying the Kronecker delta, because the Kronecker delta just picks out the major diagonal where the row is equal to the column. So everything's checking out here. The operation of lowering and raising are inverses to one another, and the corresponding linear operator, the corresponding matrix, are matrix inverses of one another. They're matrix inverses of one another because when you multiply them out, you get the identity matrix, which corresponds to doing nothing. Isn't that wonderful? Stop there. Stop.